And our next speaker is Stuart Bale, and he's going to be discussing the Lunar Surface Electromagnetics Experiment, LuSEE.
All right, can you see that?
Yes, I can.
Is that the presenter view?
Yes, it is. Perfect. Thanks.
Okay, great. Okay, so I'll give a quick talk here about LuSEE, the Lunar Surface Electromagnetics Experiment. We have a big team. These are some of the lead people on the team. Um, LuSEE is an instrument that was selected in 2019 as part of the LSITP program. So these are payloads that are destined for the CLPS landers, the Commercial Lunar Payload Services landers. We're under contract from Marshall, from the PMPO at Marshall, and we're in development. We've got, in fact, one of the payloads built, essentially, almost built. And when I say one of the payloads, so as a recent development, the LuSEE program is split into two separate payloads. So, and this is driven a little bit by mass constraints on the CP12 mission, which is right up against its NTE for mass to the Schrodinger basin, and by our desires to have a really radio quiet environment as well. So the two payloads are LuSEE Light, which we're calling LuSEE Light, which is manifested on the CP12 mission to the Schrodinger basin with the Prism 1B payloads and a cold arm, a tech demo robotic arm. And the physics of LuSEE Light is essentially the stuff we heard about this morning. The surface plasma physics, the interaction with the solar wind, plasma waves, DC electrostatic potentials. We should be able to measure dust impacts. And importantly, we're coordinating with the litmus instrument, which is also manifested, which is a Prism 1B payload manifested on CP12. And that's a magnetotellurics instrument where we plan to have a hardware interface with them. And then LuSEE Night is an instrument that's focused on low frequency radio astronomy, sort of below 50 megahertz. I'll just say a little bit about that at the end. It's not heliophysics, but and that is, well, it's not primarily heliophysics, and that's a major collaboration with the Department of Energy, the U.S. Department of Energy, Brookhaven National Lab and Lawrence Berkeley Lab. The important thing about LuSEE Light is that it'll be a standalone system that will operate through the lunar night with the lander powered off, and that's for electromagnetic cleanliness reasons. Okay, so this is LuSEE Light. LuSEE Light is primarily leftover hardware from Parker Solar Probe, the European Space Agency Solar Orbiter, and the Van Allen probes instruments, and I'll show you some of that hardware in a second, but it's basically got a search coil magnetometer, a flux gate magnetometer, and a voltage probe, and a stack of electronics, a low noise power supply, a magnetometer, electronics board, a radio frequency instrument on a computer, some biasing controls for the electronics, and DSP engine, the digital fields board. This is all the electronics, all solar probe stuff. So the idea is we'll measure the fields, electromagnetic fields, at a regular cadence of almost 300 samples per second with a burst cadence of 150 kilosamples per second. And we'll have some capability to make measurements of the ionosphere, the thermal noise line in the ionosphere, up to a megahertz or so, and some radio emission spectra up to about 20 megahertz. So this is really solar probe hardware, and I think I have a picture on the next slide of the hardware. No, I have a combination picture. So this is a notional lander. We don't have a real lander yet, but so we'll have a 2-meter mag boom that pops off the side with a flux gate. We'll pop this V3 antenna, which has a voltage probe at the end of it, about 6 meters up off the top deck of the lander, and a search coil magnetometer on a 1-meter boom off the side. These are the litmus electrodes, which will be deployed out to 20 meters or so from the payload, 20 meters on the side from the payload, and we'll make the voltage measurements for the magnetotellurics experiment. CP12 is destined for the Schrodinger basin. There is not a definitive site selected yet, landing site selected. In fact, there's a telecom that I just missed I'm missing right now to discuss this, but we're looking at places that are in the south east rim of the Schrodinger basin crater, so near the outer ring of the crater, around, I think the notional landing site is around 79 south and 140 east or so. And that's really driven by the magnetotellurics and the seismic instruments on the payload. As far as we're concerned with LuSEE Light, just getting to the moon, the solar wind will be everywhere, right? And so the interaction with the solar wind, the changing zenith angle of the sun, we'll see that no matter where we are. Okay, and this is just a picture of some hardware electronic stack from Parker Solar Probe. This is the actual flight model search coil we have, a magnetometer, and this is the boom that we're going to use to pop up and make the vertical measurement. Okay, LuSEE Light is motivated differently. LuSEE Light is motivated by an attempt to make kind of a pathfinder measurement of the low frequency spectrum below the ionospheric cutoff that will be could be important for radio cosmology. Will certainly be a best case measurement of the galactic synchrotron spectrum at low frequencies. We'll also see the sun, the sunset, the quiet sun, presumably. We're going to try to make a measurement that's about a part in 10 to the 5 on the galactic foreground in an attempt to constrain what's called the dark ages of radio cosmology, which is a 21 centimeter signature associated with the formation of the first recombined matter, basically. After the Big Bang, when matter recombines and becomes neutral, there's a 21 centimeter spin flip transition that absorbs the CMB and creates a signature there. So it's a stretch measurement, but I think it's a powerful motivating force for us. And this is our notional design for LuSEE at night. LuSEE Night, so we'll have a lander that we are accommodated on as a standalone device. We're basing our kind of thermal design on the FSS instrument, which is a Prism 1B, a JPL-led Prism 1B payload, which is also a standalone instrument. So we'll have a box with our electronics inside, with a battery, a big battery, 50 kilogram battery or so, our own comm system, which it looks like will be provided by JPL, a user terminal. We'll deploy our antennas out into cross dipoles with probably around a 50 megahertz bandwidth. They'll be mounted on a turntable so that when we have sunlight during the day, when we have full power, we'll have our own solar panels. When we have full power, we'll be able to rotate this around to change the orientation with respect to the regolith and try to understand the coupling to the moon below us, and our beam pattern on the sky. And so this mission, this thing is, as I said, it's a big collaboration with the DOE, the Department of Energy, Brookhaven National Labs, and LBL Lab, who are going to put in substantial effort and funding to this. We are going to go on the CS3 mission, which is the mission that delivers the Lunar Pathfinder, the ESA Lunar Pathfinder relay satellite into orbit in early 2025. Our early 2025 landing date is determined by the outer planets. We want to have the outer planets, which are also radio sources in this bandwidth. We want to have them below the horizon as much as possible while the sun is set. So it's when the sun is down, we want the outer planets to be down as well, so we can just see the virgin sky above us.
1 minute.
Okay, this is my last slide. So the lander will die after commissioning. So we'll get to the ground. We'll make sure everything is working, and then when the sun sets, the lander will never wake up again. And that's what we want. We want that because we don't want to have switching power supplies and all kinds of other uncontrolled electromagnetic sources operating on the same platform. So we'll be alone on this thing. A landing site is under study right now. We have a group, NASA's leading a group to study this. We're looking at mid-latitudes, slightly south of the equator, so we can have one side of our platform darker than the others to put radiators on, and we can have the Lunar Pathfinder relay satellite overhead as much as possible. And that's my last slide.
Thank you, Stuart. I have to say I was not expecting to see cosmology in one of these
Yeah,
talks.
well, I didn't. Yeah, everyone covered the heliophysics this morning, right? It was great. There was enough of that.
That's right. Let's see. There is a comment in the chat for you.
Okay.
And let's see.
See if I can see the chat window.
It's saying that Milan is happy to see that electric fields are receiving attention.
Yes, electric fields are important.
Yes,
Agreed.
and that magnetic
Completely.
fields are a derivative of the phenomena. Yes, but magnetic
Right.
fields are also very important as well. So how do you see this impacting, or some of what you'll be learning from this impacting some of the Artemis missions?
Well, I think, okay, so as far as the heliophysics, we're going to see the sun when the sun is in the sky. We're going to see it, and we're going to have terrific measurements of solar radio bursts associated with solar flares and with CMEs and that sort of thing. When the sun goes down, we may see some stuff reflected around the limb, but we should probably just see outer planets and astrophysics. So it's going to be both, I think.
Okay.
Maybe that didn't answer the question, but
A little bit. So do you think with the radio bursts, do you think you'll have a pre-warning of any SEP event that's going to be impacting some of the lunar sites that astronauts will be at, or any of that
Um, I,
activity?
I don't imagine that we'll have real-time data. We're
Uh,
talking to a relay satellite, and so we're going to have our ConOps will be certainly the nighttime. At night, we won't have any comms at all. We'll just sit and operate. When the sun comes up, we'll power up the comm system, charge the battery, and maybe rotate our antennas around,
mhm.
and that's when we'll get the data off the lander.
Okay, awesome. Well, thanks very much. I appreciate you
Sure.
giving this talk.